Hello everybody, and today I am going to make the editorial video of problem tree retrieval from July lunchtime 2022 division 1. So I hope you understood the statement and we will go subtask wise. So let's start from the first subtask for 13 points, which is tree is a path. So what does a path mean? The path means that tree is something like this. Okay, so there are exactly two leaves in the path and each node has at most two uh, childs or two adjacent nodes. So basically you are given two integers. So first is the one of the nodes, which is kind of a leaf node. Okay, so basically the approach for this will be like you just do query the whole set of so nodes. So you will get one leaf node, let me say that x, and you will get the sum of nodes, leaf nodes, but you know that there are only two leaf nodes because this is not an isolable node. So for this set of path, the isolable nodes will be only the leaf nodes because this is not isolable, because if any one of edge is removed, other node is always visible, but these are isolable nodes, right? So you know that you will get some node x and the sum of nodes, because there are just two nodes, it will be x plus y. So as you find the value of x, just keep this node as the key node, and now you just query, got the value of y, so you know that the root will be y, the other leaf will be y. So you just remove the leaf for the next time and you ask query this with removing that node y. So you will again get some sum as x because plus y1, because this node is still there, so this x will be there, and this new node y1 will be there because y is removed, which will be an adjacent of y, right? So now you found the value of y1, so you know that there is a edge between y and y1. You remove this node and similarly you keep doing, and when the last x is remaining, you know that the previously removed node has an edge with x. So this will give you 13 points. Then here we finish with the first subtask. The next subtask is sum of n over all test cases does not exceed 100, and the third subtask is number of leaves is just 10, and the sum of n is just 500. So my approach for both of them would be the same, and so I will explain my approach and let you know that how it works for both. So my approach is that we have some tree. Okay, let me have some tree. Okay, so here the current sum, or let me say it as x1 x2 x3 x4. Let me remove this part. Okay, x4, the current sum is x1 plus x2 plus x3 plus x4. The tree is all the nodes, like all the nodes in this set are we going to be queried. Okay, so we query, we found this x1 f2 x3 plus x4 as the nodes. We don't know how many x's are there, of course, and this is an example, and we'll get the node which will be a leaf node because we are taking all the whole of the tree. Let me say x1. So when I know that this node is x1, the next time we remove this node x1, add it in some set, and we have it x1. Now we query again, we'll know that we will get some node x5, right? So the new sum will be sum 1 equals to x5 plus x2 plus x3 plus x4, right? This is the first case, and the second case is, suppose this node tree is something like this. This node is x1 x4 and this node is x1. Okay, and this node is removed. Okay, so this node is removed and this is x5. So x5 is not added if you query the whole tree, because the remaining part of the tree, because x3 is still leaf nodes, x5 has not become leaf node, this will not be isolable, right? So the new sum will not include x5. When the new sum does not include x5, we know that that is not a parent. So we know that x, we don't know the x1 parent of the x1 because we are removing the leaf node. We're expecting to find the parent, and then we just have then edge with the parent, and then we find the parent of the new parent, right? And that's how we find the tree, but we don't know the parent of x1 now, right? So these are the two conditions happening. For the first condition, it's seen that x1 if removed and this new node added xy, then we can find the xy because it's nothing but xy plus, so we subtract it, this is removed, we know the value of x1 as x1 is given by them, so we find the value of xy. It's easy. So now the thing is, when we don't have this xy, so now we as usual put the x in the set. So now what does the set means? These nodes have been removed from the set or from the tree that we are querying and still have not got the parent. So when I get some parent, okay, so let me just clear this off. Yeah, so this is our tree, right? So now when we know that, suppose this node is queried, so we have a set and we have x1 over here, let me say x1. So this node is not there now in the tree, and now this node is there, x2. So now I know that x2 when is removed, x3 is added, so I know that there is an automatic edge between x2 and x3, but in the next query we get to know that. But now we have x1, so we just need to check if there is x3 and x1, does they have an edge. Similar another contrary case can happen where this is here, it was not a parent, right? This and this are not, it's not parent, but here if we remove this, now suppose this is a new x2, you know that here x3 comes, we know that x2 and x3 will be surely x2 will have surely x3 as its parent. But what about this node x1? It is also having a parent. So now we need to check. So what do you need to check? When such node comes, when it becomes a root node, okay, so I know that this is removed. Now when this node is also removed, this node, the new leaf node, not root node, this becomes the new leaf node. So when we find this new leaf node, we just need to check that how or what are the other child possible children, or who are the other possible children, because they are also removed and they have not been connected with the parent, right? They have not been found yet. So how do we find? We know the direct the last removed child, and we find that, okay, then now this child is remaining. So what we do is we query now. I know that this is also in the set, so okay, suppose this is also in the set, just not putting an edge or a dotted edge, that these are removed and this is in the set. I know that this was removed previously, so this is a child. Now when I know check this, I take all the remaining tree. What is the remaining tree? These and this node are removed, so the remaining tree is this, okay, and this node will be added. So when this is such a case, I know that this is a leaf node, so this will be added. The sum, initial sum, is the current sum of this node, this node, this node. I know that this is added, so its parent will be removed because this becomes a new leaf, and parent is not isolable, so this becomes the new leaf, and whichever is the parent, that value is removed. So we just find, so it's like sum equals to x1 x2 plus x3, and the new sum we find with this node is the current, let me say x4, plus sum minus its parent, right? So we find that we know the value of x4, we know the value of sum, and we just need to find the parent, right? So this is how we find. And if it's not its parent, then some other parent will be removed, right? And probably that won't be its parent because it's a child, right? So basically leave that case now. So I know that this does not have an edge. So for this node, I know that this node will be added and this node will be removed. So we know that this both are not a child, what we say, a child parent relation, are not adjacent to each other, right? So the second option is that now we found how to find if there is an edge between both, right? And so now when you add some, it's not his child, then you know that it's possibly this case. Okay, and here is your node. When you remove this, you know that this is also removed. So basically this is in the set. Let me say x1, so x1 is in the set. This x2 node is removed, the last previous, so let me say x2 is added. Now you know that this is the new node, so previously added will be removed, so x1 is removed, x2 is removed. Now you need to check with x1. You check and you see that this node value of no node is removed, right? So you know that no parent is found for this, right? Because value of no node will be removed, and that will be true, because if some node's value is removed, that means it's already a parent of that node. Because if this is only remaining, then if you add this and the value of this is removed, then you know that this has already found its parent. Okay, so basically it's just like you have maintain a set which contains the nodes whose parent are not found. We loop through the leaves, or we loop through the current set, and we each time we remove one element which is a leaf of the current set, and when a new leaf becomes, we just check it with each of the nodes in the set, and we check that if that is node is the child of the current new leaf formed. And this is looks like order of n square, because for each node we can have an each node query. But for the next subtask, you can see the number of leaves are just 10 and n is just 500, so number of leaves are 10. Okay, so what can you say about the tree is something like 1 2 3 4 5 6 7 8. So what can you say about the tree? The root is always the 1, right? And the number of children can be greater than or equal to 1. So when you know that there are at most 10 leaves, so what can you say about this number of nodes in the leaf in the set? What is the maximum number of nodes in the set? You know that if a node is added over here, and if it has two childs, then when this node is added, it loops these two childs and removes them, and this node is added. Right? Every time a new node is added to the set, it's only 1, and the number of nodes that are removed will be greater than equal to 1. Because when a new node is added, we just remove the case of the leaf nodes. Okay, so when its parents are added, we know that when they are added, the leaf node, at least one leaf node is removed, right? Because there's a possibility that this has only one parent and the parent has only one leaf node. When this is added to the set, this is removed. So starting, suppose there are 10 leaves, and the next time if a parent is added, greater than equal to 1 one nodes are removed, because one will be a direct child and the others might be removed previously, and we check and we remove that. So the set size cannot increase by more than 10, because there are just 10 leaves. So for each node, there are n, and for each node we do at most 10 checkings with the set. That for the set size will be only 10. So like for each node we check each node in the set, right? And the set size is 10, so it becomes n into 10 and plus n, or something like that. Well, the n is constant, yeah, it doesn't matter. So it becomes n into 10, and n is just 500 into 10, which is 5000. So we can complete this in 5000 queries. So this is my solution for subtask 2 and subtask 3, which will give you 43 points, and this won't be done, I guess. I don't know about that, but let's leave this, and this is quite easy for doing. And the fourth subtask, the final solution, 100-point solution. So here we are a main thing will be, we have know the tree over here. This is some tree, and we add some node in this tree such that it is connected to some of the leaf or some of the node in the tree, directly connected, right? So I know that there is some tree, I know that the edges also I know about this tree. This is some tree. Okay, so I know that there's a direct edge from this node to this node. Okay, and this node I need to add to the tree, so I just need to find the which node is directly connected to the current node. I know that about that node, I have found the values, like the parent of that node I have found it, so it's connected to the current tree, it's not getting disconnected. I will only have a one component. So how do we find this? Okay, so suppose you have some tree. Okay, and now you have to add some node. Let me say over here. Okay, so you know the current tree, and what you need to do is we'll binary search on the heights. Okay, so the height is 1 2 3 4 5. The current tree height is 5. We binary search on heights, so let me say the current is 3. We binary search and we take the 3 all the nodes till the height 3 or depth 3, and the current node which are we going to add, let me say as x. So what will be the value of this? It will be it will be x1 plus x2 plus x3 plus x4, right? Let me say this as x1 x2 x3 and x4, so it's x1 plus x2 plus x3 plus x4. But x is directly connected to some node, so I know that that node will not be isolable now. So now I know that this will be the sum, and the new sum with this x, we know this sum, so we will not query this sum of course, and the new sum with current node x will be x plus sum minus sum it's of its parent minus some ancestor, not its parent. Let me say a ancestor. Okay, so it will be something like that. So we find its ancestor, right? So here its ancestor will be this value, so I know that its ancestor is also a parent, like a parent is also ancestor, right? So I know that we find the value, and now I found, now there are two options, that I found its ancestor, I don't find its ancestor. So when do I don't find its ancestor? Here I find its ancestor. Remove this is removed, this is not isolable now. But suppose I query on the depth, not this depth, I query on depth, this depth 4. So I know that the sum will be x1 plus x2 plus x3, this node is not there, x4 x5 x6 x7. This sum I know, sum 1 will be sum of these plus x, because I know that this node is not isolable, and this new root isolable node is added. So x plus sum, right? So when I know that it's x plus sum, I have came to down and I need to go up, right? And if I know that I find some of its ancestor, then I know that I need to go more deep, and suppose I find this ancestor over 3, so I will go more deep in the range 4 to 5. Suppose I binary search on 4, I don't go ancestor, so I go up, and so I know that now there is no binary search possible because r is greater than l. So here I know that ancestor is 3. Some no ancestor which I found on 3 is the answer. Else if I find more, suppose I find 2 first, so I find that this node is the ancestor. If I binary search on 2 depth 2, this node is ancestor. Now I binary search on depth 3, this node is the ancestor, then this becomes a new ancestor because I want the lowest ancestor, so that because lowest ancestor is the parent. So using binary search I find the lowest ancestor of some node x which is directly connected to it, and I just add it to the x. We do this recursionally and we keep adding the nodes. Okay, but now how do we satisfy the condition that the current tree is there, then this node that is getting added does not make a new component, that is, it does not have some node here and here which are not connected over here. So I just want a single component, a single tree. So how do we do that? So basically we just use the thing that we get a node right from them, so we just consider it, so we just do n operations to find the order of nodes. So basically we just take the whole set, like the whole set. Okay, So here we will get a leaf node, we remove it, add it in the array. Let me say x, then we get this node, add it in the array, x1 x1 x2, then we get this added in the array x3, then we get this added in the array x4, then we get this added in the array x5. Similarly we keep doing, and then we suppose get 6 x6, then we get this x7, or let me say get this x7. Similarly this will be x8. So basically here x8 will be the root or the last element of the current permutation. This will permutation with each node occurs exactly one. This x1 will be the node given by them. Like so I query the remaining tree, I get the node, I know that this node is one of the isolable node, that is a current leaf of the current tree, so I remove that node and add it in the order. So I know that x7 will have an edge from x8, else x8 has not become an isolable. Similarly, when we have x6, it will be sum of x7 or x8, else they are not possible to become isolable, right? So following things work. So, right, so basically we find so new tree will be like something like this, then we have this, then we have this, and some node is added. When some node is removed, I know this is the leaf. Okay, and I know that if this is a leaf, then its parent will be present. Okay, so this formula we get the tree, and we'll get some random node, and we'll get some random permutation. But here we know that if this node is occurred, then I know that this is the leaf of the current tree, so its parent is still remaining and it will come over here. So we loop from behind to find it out. So it's nothing but order of n log n. So and this current n doesn't matter much because it's not going to be exactly log n every time, right? You starting in the start, you have a leaf of just height 1 and log n is just maximum 10. So in maximum 10 queries for each node, that is 10 to the power 4, you can solve the current problem. This is how we find the solution for this problem, and I hope you got the solution. Thank you for watching my video. Do forget to like, subscribe and click the bell icon.